Okay, welcome everyone. Good evening. I am Beth Menzing. I teach at Strathaven High School, and our program this evening is going to consist of 3 speakers, followed by an opportunity for you all to ask questions if you would like. We are going to record the session, and then we'll post the recording via email in the next few days. But before we get started, we know we just entered a lot of people into the session here. Could you write in the chat your high school, your school name, and how about your mascot? Go ahead and in the chat, because we're going to be using the chat tonight. So we want to make sure everyone found the chat, and that if you could enter your high school and your school mascot.
Yeah, the chat is definitely going to be active. So we want you to be able to find that chat box.
Welcome, Haverford. Yay. We got some Delaware County friends here. Cheltenham up north. Upper Perk. Nice. Cheltenham again. Got the Knights. Perkman Valley, Garnet Valley. All right. We got some locals too. Germantown friends. Welcome. Haverford again. Yes. We have students from Radnor, Springfield Township, Cheltenham. This is awesome.
I think we got at least a dozen schools, if not more, right?
I think so. I didn't actually count, but maybe even more. Hey, Martha. Yay. Well, I think at this point in time, we're going to get started. Our first presenter is Miss Lee Notaro from Moravian Academy. Lee, thank you so much for joining us.
All right. So Beth might have already mentioned, my slide too many. Beth might have already mentioned that we are going to be having 3 separate little mini sessions here tonight. We are going to be having a session on multiple choice strategies, which I'm going to be talking about. We're also going to be talking about sampling and experiments, because there's a lot of vocabulary there that can trick people up. We're also going to be talking about probability, and we're going to have some time for questions and answers at the end. So in terms of the multiple choice questions, I'm going to share with you some information that you probably already know about. The multiple choice section takes 90 minutes, and there are 40 questions. Each of those questions has 5 answer choices, A through E. And generally speaking, they start off a little bit easier and then get a little bit more challenging in general. So keep that in mind. And this is really important, there is no penalty for guessing. So if you don't know an answer, you don't want to leave a question blank. You want to make sure that you actually do answer the question. However, there are some strategies that we're going to talk about to help maximize your chances of getting that question correct. So there's a couple different strategies we're going to talk about tonight. One is called annotate the question. We also have annotate the answers first. Then we're going to talk about something called Scratch One, Choose One. This is my personal favorite. And then we're going to look at an example where we combine all the strategies together. So let's talk about the first strategy, annotate the question. And so you might not be used to writing on your questions when you see them, but you should definitely write on the question. You should make note of what the numbers are and what they represent, possibly label them, X bar if it's a sample mean, mu if it's a population mean. You definitely want to underline the question so you know what it is that you're being asked to find, possibly circle any keywords like less than or greater than. And so let's take a look at how this strategy could be applied on a specific question. So here's a question that we're going to take a look at. I'm going to read it to you, and I want you then in the chat to share what you think you might underline or circle. So studies have shown that approximately 10% of the US population is left-handed. A research study selects a random sample of 40 people in the US and asks a number of questions about their lifestyle. One of them is if they're left-handed. Which of the following shows the probability that exactly 5 of those in this survey report that they are left-handed? So in the chat right now, I'd like you to post something that you might have circled or annotated in this question. Could be a number, it could be keywords. the sample size, noting that n equals 40, p equals 0.1,
How did n
exactly
equals
5.
40?
Yeah, definitely. Those are things that you'd want to annotate, possibly random sample of 40. Let me see what I've chosen here. So 10% and 40. Notice that you might even write down the notation that it's p equals 0.10. N equals 40 is what a lot of people already said. And then also probably that exactly 5 of those surveys in the survey report that they're left-handed. And you also might want to make a note to yourself that it's a binomial situation. And you might be wondering, why should I really do this? Well, let's say that you choose your answer or you've done your calculation and you're like, wait, it doesn't match any of the answers here. You've now left yourself some notes so that later on, when you go back into that question, you can actually get back into that question a little bit faster because you've made these notes and left these notes for yourself, for your future forgetful self. All right, let's take a look at the second strategy, which is to annotate the answers first. So let's take a look at that. We're going to annotate the answers first. And you might say, well, why would I want to look at the answers first? Well, sometimes it's actually better to take a look at the answers because they give you a clue as to what you need to look for within the stem of the question. So that's what I'm saying. It helps you to find what you need within the prompt. So let's take a look at this. Now, this is a question that there's more information above this that I haven't shared with you. We'll take a look at that in a little bit. But here we are just looking at the answers first, and we notice that the answers are for different procedures, right? And so we might ask ourselves some questions related to this as we take a look at the question in a moment. We might ask ourselves, are we working with one sample or two? Because some of these answers have the words one sample in it, some of them have two samples in it. So we might want to think about that when we go back up and look at the question. The other thing that we notice is that a lot of the procedures that are listed here are either for means or proportions. So that might be something that we want to look at as well. Although I'm guessing it might be related to a proportion because I do see something about 20% here. We'll find out in a second. And then this last one, let me go back one. This last one, is there a two-way table? That's the chi-squared test of homogeneity. So let's take a look at the actual prompt that was above this question to see if we can figure out which one of these 5 it would be. So we have to ask ourselves these questions as we take a look at the information. So here's the beginning of this prompt. In the past, 20% of customers returned to the specific department store K to redeem their K cash. If given 2 weeks to redeem their K cash instead of 1 week, will the proportion of customers who redeem their K cash increase? Is it better to have 2 weeks instead of 1 week? 250 randomly selected customers were given 2 weeks and 80 of them redeemed their K cash. So assuming the conditions for inference have been met, what procedure will be used to determine if more than 20% of customers would redeem their K cash within the longer time frame? So let's think about this. I'm going to ask you some questions now in the chat related to this. Are we working with one sample or two samples here? So in the chat, you can give me the number 1 or the number 2. Are we working with one sample or two samples? Might have to go back here just to take a look a second. Yep, one sample. So we're working with one sample. And there definitely was no two-way table, that's for sure. And as you said, we're working with one sample. So right now, I know that I'm working with either a one sample t-test for a mean or a one sample z-test for a proportion. So here's my last question for you in the chat. Are we working with means or proportions? Means or proportions? A z-test for proportions? Okay, the 20% would indicate that we're working with proportions, and we are working with proportions. So the correct answer for this one is answer B. So identifying those key characteristics, one sample or two, means or proportions, and is there a two-way table, would help you to figure out what is the correct answer for this one. So let's move on to our third strategy. And this is scratch one, choose one. And this is where I think it's important to notice how the answers are alike and how they're different. So what makes the answers alike and what makes them different? And that can help you to eliminate 2 or 3 answers in this way. So, and I see that there's a direct message chat. We'll answer that later on at the end. 2 or 3 answers can be eliminated by using this strategy of scratch one, choose one. And since there's no penalty for guessing, by eliminating 2 or 3 answers, you've definitely increased the chances of getting the right answer. So let's take a look at how this can be applied. All right, so here's where we're going to use the strategy of scratch one, choose one. And so here's the scenario that we're going to be working with. To determine the proportion of trees that are infested with a spotted lanternfly in one region, a 99% confidence interval is going to be constructed. It's estimated that there are 250,000 trees in the region, and we're going to do a random sample of 500 trees to see if they have spotted lanternfly activity. And actually 120 of the 500 trees had spotted lanternfly activity. Based on this study, which of the following expressions could be used to create a 99% confidence interval for P, the proportion of trees that are infested? So let's take a look at this. What are the answer choices that we have here? So here are the answer choices that we have that go along with this. And what is something that you notice is the same about all these answers? So go ahead and type something related to that in the chat. What is something that you notice is the same across all of these answers? Okay, I've got some people saying 0.24. Yep, the 0.24, that's the sample proportion. That was 120 out of 500. They're all using the same general formula, right? But notice that some of them have 1.96 as a critical value. Others have 2.576. And down here we have 1.645. So if we can figure out the correct critical value, we might be able to eliminate some answers. And the correct critical value for a 99% confidence interval is 2.576. You can get that from the bottom of your t-table in that infinite degrees of freedom row. So I'm going to actually eliminate answers C and E. All right. From here, we might take a look at the formula structure that's actually on the exam sheet for that standard error of the estimate. And notice in the denominator, we have our sample size. Our sample size was not 120, so we'd eliminate that one. And then notice that this formula has P hat here, our sample proportion, which was 24%. So again, we can eliminate choice D, and we know the correct answer is choice A. I'll go back there for a split second. Choice A. So, but noticing how the structure of these is the same and how they're slightly different will help you to eliminate some answers and at least scratch one or two before you choose the correct answer. So last but not least, let's take a look at combining all of these strategies together, annotate the question, annotate the answers first, and scratch one, choose one. So here we're going to talk about the correct interpretation for the slope. And I know a lot of these sentences are kind of long, but notice that they have the same structure. They all start off with for each additional 1 centimeter increase. All right. And then after that, it varies a little bit. And notice that the numbers are a little bit different. So we're going to kind of annotate this answer and also notice the structure. And if I could identify what the slope is, that might help me to figure out which of these to eliminate. So noticing the slope, also noticing that some of these have the words increase and some of them have the word decrease. So if we can figure out whether the slope should be positive or negative, that would help us as well. So here's the computer output, and we're trying to predict height from femur length. And one of these numbers in this computer output is our slope. In the chat right now, type in the number that you think is our slope. What number is our slope? We've got lots of numbers in this, and knowing which number is which is really important. The 1.654, yeah, so if we take a look at our answer choices, we saw that 1.654 happened in 3 of these answer choices. So that is our slope. So that means that we're going to be able to eliminate answer choices, actually also C, because of the word decrease here, and E because of the word decrease. So right now, we know our slope is 1.654. We got rid of choices C and D because of the words decrease, because the slope is positive, not negative. And we can also get rid of this one because we know that the 97.8 was not the slope. So we are now down to answer choices B and D. And so now we need to think about how we interpret slope. So think for a moment, slope is change in y over change in x, and we're predicting height from femur length. So y is our height, femur length is our x. So height divided by femur length. And so if you take a look here, we're talking about changing the height for every 1 centimeter increase in femur length. So the slope is going to be 1.654 divided by 1. So that is changing the height. Predicted height will increase by 1.654 centimeters for every 1 centimeter longer in femur length. And that means we'll eliminate answer choice B. And we have answer choice D as the correct answer, as somebody already pointed out in the chat. So those are the multiple choice strategies. Annotate the question, annotate the answers first, scratch one, choose one, and possibly combining all the strategies together. And I definitely want to remind you that you always want to do your best to make an educated guess. And you can do that by using these strategies. I am going to stop my screen sharing and turn this over to our next presenter, which is Bob Loschel.
Thank you, Lee. Hey, friends, can we get a couple snaps or claps in the chat for Ms. Notaro for her wonderful presentation? Thank you so much, Lee. And as I get myself set up here and I won't be able to see the chat, please bear with me. Whenever we move around, it gets tough to see. So there we go. So good evening, everybody. So hopefully you can see my screen okay. I think that I'm okay. Lee, can you just give me a shout out that I'm okay?
You are good.
Thank you very much. So folks, for about 20 minutes, my segment is on sampling and experimental design. My name is Mr. Loschel. I teach at Happer Horsham High School. And I just want to point out that each of your 3 presenters tonight, not only are we all AP statistics teachers, we're also readers of the AP statistics exam. We've all been to the reading many times, and we've all been doing it for at least 10 years. So we come from with a bank of experience here. And this picture here is maybe some of your favorite AP Stat teachers who were organizing for barbecue one year at an AP Stat reading. So we hope that you get something out of today's presentation from our expertise. So this will be about its sampling and experimental design, and this is the most wordy narrative portion of the course. So I'm going to do a brief review of as many terms and ideas as I can, and there will be opportunities for you to share your ideas in the chat. So let's dive right into a question. Administrators at Villanova University are considering raising the student activity fee in order to pay for improvements to athletic facilities. In order to keep costs low, they plan to conduct a convenience sample at the next basketball game. First 50 students who enter the stadium could make up the sample. Now, I'm going to ask you the question, but I'm not asking you to do it in chat because that'd be a lot of writing. But just consider the question here. Why might such a sampling method be biased in producing an estimate of the proportion of students who support raising the student activity fee? And I'll tell you from my experience as a reader, this type of question, students often write a lot. And some of it can be really good stuff, but sometimes it's off base. And I want to guide you towards how you can assemble a good response here. So let's deconstruct what's going on. And first of all, keep in mind our goal is to produce an estimate of the proportion of students. How good of a job are we doing in estimating the proportion who are okay with raising the fee? So let's deconstruct things. So I'm about to show you a multiple choice question. Let's call it choose the best. But follow my instructions here. When you see your favorite answer, don't type it in the chat right away. What I'd like you to do is type it in your keyboard. Don't press enter yet and wait for me to say enter. We'll do it all at the same time, and we'll get this cool little waterfall effect. And this actually comes to me. Lee actually taught me this trick. So why might such a sampling method be biased in producing an estimate of the proportion of students who support raising the student activity fee? So I'm going to show you 4 choices here. Hold on to it in the chat, and then we'll wait. So first of all, not all students like basketball. Sample size isn't big enough. The students in the sample may be different other students. Or D, only a random sample can give accurate information. So take a moment, press your favorite answer, don't press enter yet. And in 5 seconds, we'll all press enter. 4, 3, 2, 1, enter. Let's see what we say. Oh, wow, we have all kinds of answers. I actually have seen all 4 letters there. So let me tell you the correct one first, and let's deconstruct the others. I did see lots of C. I appreciate you, Lee, for that. Saw lots of C, and C is the correct one. When we talked about producing an estimate, we are choosing the first 50 students who enter the stadium. And the students that we survey may be different from other students. It's true that not all students may not like basketball. That might be true, but that doesn't tell us anything about an estimate. Sample size isn't big enough. Well, 50 is pretty good. We know from different techniques that oftentimes a sample size of 50 may not be ideal, but it's certainly not super small. And only a random sample can give accurate information. Well, there's other ways. I wish it were a random sample, but that alone isn't the reason that we have a biased estimate. So let's dig deeper into this idea of bias. Approaching this task, what does it mean to have a biased estimate? And why is our sampling method biased? And just what are we trying to estimate anyway? These are all the things that you need to think about within your response. And what you don't want to do is use super statistical language without supporting it. In fact, you can write an explanation here that doesn't use a lot of vocabulary at all if you can speak in plain language. All right, so first of all, this is very important. I'm going to show you a picture that tells you the essence of statistics. You understand this picture, the keys to the kingdom have been given to you. Here it is. Ready? Boom, there it is. Using a sample to tell you something about a population. That's it. It's target practice. How well is our sample hitting the target of the population? And if it's not, we got to say why. And the idea of bias is if the design of a study, of a statistical study shows bias, if it systematically favors certain outcomes. Are certain outcomes being favored by asking students who enter a basketball game if we're trying to talk about all students? And I hope you agree they are. So some pro tips here. I use a phrase in my class that's called word salad. Word salad means you're just throwing words, statistical words out there like, well, you can't do this because it's biased and blah, blah, blah. Try to speak in plain language. That's the best piece of advice I can give you. So bias, if you use that word, it has to be accompanied by, we're going to overestimate, we're going to underestimate, and why? Context, context, context. What is this problem about? Don't lose sight of what the problem's about, and use fancy language carefully. Don't use a whole lot of words like confounding variables and all this other stuff if you don't support them with examples. Stay on point, don't ramble. So let's take a look at a model response here. Here's a model response, model solution. These 50 students may not represent the student population as a whole. For example, they may have more school spirit than the population as a whole. So they might be different than the population in some way. They have more school spirit. There's a plausible reason why they might be different. They're very rah-rah about Villanova, as one should be. Therefore, they may be more likely to support an increase in the student activity fee because they're very much into the school. And if they do this, the administrators may overestimate the proportion of all Villanova students who might support an increase in the student activity fee. So not a lot of fancy language in there, but connecting dots. So connect the dots and use plain language. Okay, let's try another one here. Yeah, I agree, Lee. Word salads take too much time to write too. All right, here's a new survey. Same idea. Because of the large number of students at the university, a second method the administrator is considering consists of using a computer with a random number generator to select a simple random sample of 500 students from a list of 2,000 students. Describe how to implement such a method. Now notice here with randomization, sometimes you're given choice, but this one says you have to use a computer random number generator. But keep in mind, we have things like the hat method, which we're going to go over here. How should we implement it? So some randomization methods that you could use. If you could use the hat method. Here you have to use a random number generator, but the hat method would be good if you're allowed to. Shake up the hat without replacement, give a stopping roll. And one flaw I see students try to do is they number the subjects. We're going to number the people from 1 to 2,000. Well, if you have their names, just take their names, put them on slices of paper, and put them into your hat or your bucket or whatever it is, and shake it all up. Numbering the students takes time, and then you have to worry about repeats and that sort of thing. And a stopping rule, tell me when to stop. Or if it's technology, define your domain with unique numbers and a stopping rule. Here we have 1 to 2,000 students. I'm going to pick unique numbers until I get enough people to be in my survey. And table random digits is a thing. In early years of the AP exam, it was on there. I haven't seen a table of random digits for years. Be somewhat familiar with it, but that's a last resort. We don't want to use a table of random digits. Okay. So one more thing about this question. Here's another prompt. Same scenario. Another administrator suggests that perhaps stratification by type of student, undergraduate versus graduate, may provide a more precise estimate of the support for student activity fees. Under what circumstances would stratification by type of student provide a more precise estimate than a simple random sample? Why should we stratify? So keep in mind, this is a choose your best stream. So I'm going to show you, I think this one has 3 options. Hold on to your response, what you're going to do, and then we're going to press enter all together. So here's your 3 choices. Why should we stratify? First, if we want to make sure that everyone has a chance to participate. B, if we think that everyone will disagree with the activity fee. C, if we want our results to be more accurate. Or D, if we think that undergrad and graduate students may feel differently. So hold on to your response. Don't present it. You're being awesome about this. 5, 4, 3, 2, 1, enter. What are we going with? Oh, look at this. It's Thursday night. We're doing great. I see a lot of D, and it is D. We stratify when it's likely that there are clear differences between the groups. And again, the other things aren't necessarily bad things. It'd be nice if everyone has a chance to participate, but that's not why we stratify. If we think that everyone will disagree with the activity fee, then maybe why are we taking a survey at all? If we want our results to be more accurate, that's a phrase I need you to stay away from. Being more accurate. There's probably another way to say that. But if we think that undergrad and grad students may feel differently, this idea of stratifying is oftentimes confused by students. So let's take a deeper dive into it. Should we stratify? If we believe there's a difference in opinion on raising the student activity fee between grads and undergrads, then stratifying is appropriate. This is also if you think between genders that there are differences of opinion, and if you think those differences of opinion may be similar within those groups. The graduate students all say no new activity fees. Undergrad students, yeah, we tend to like it. So if there's differences, but there's similarities within these groups. I do see a message here. If you could hold off till the end, we'll take care of questions at the end. Thank you very much. And Lee, if you think it's a question worth answering, just feel free to chime in. Okay. Should we stratify? And the way you stratify is you take your population, break into subgroups, and then take proportional sized random samples from each group. 50-50 or 60-40 if it's graduate and undergraduate, 60-40. We're not often asked to go that deep a dive into it though. Okay. You know what? I'm going to answer that direct message. There's someone who's asking about blocking. I'm going to do blocking in the next part. So, but blocking is not the same as stratifying, but we're going to see blocking in a moment. Okay. We're now going to switch gears to experimental design. There are a lot of similar, same language, but some different language here too. So let's take a look at this scenario here. A producer of a famous brand of sunscreen plans to conduct an experiment to compare a new sunscreen formula to the current method. Your outward appearance is not changed by either method. The company recruits 100 volunteers to participate in an experiment on a sunny day in Ocean City, New Jersey, where the participants will be asked to spend 2 hours having fun in the sun. Don't we wish we were there now? After which subjects' arms will be assessed. The questions I'm asking you, the last couple of years in the AP Stat exam, they've settled into this idea of asking these very specific questions about experimental design. That does not mean they're going to do it this year, but we've seen it multiple times now, where they ask questions like, what are the experimental units? What are the treatments? What is the response variable? Let's do this. I don't want to do all three, but impress me with one of these. What do you think are the experimental units? Take a minute and just put that one in chat. You don't have to wait for the 5 seconds. What are the experimental units here? Okay, a lot of people saying the volunteers. Okay, good. Let's take a look what we have here. The volunteers, the experimental units are the 100 volunteers. Specifically, it's the 100 sets of arms. If you could be more specific about it. The people who are the things that are receiving the treatments are the experimental units, specifically the arms. You could probably get away with the experimental units being the 100 volunteers. Be nice if you said how many. What are the treatments? The new sunscreen and the current sunscreen. So don't just say the sunscreens. There are 2 treatments. Identify them both, new and current. And then finally, the response variable. And this is one where students tend to be a little less wordy than they should be. Response variable is something we're measuring. The amount of, I said skin darkness because I couldn't think of another way to say it. The amount of skin burn, the amount of burn on your arm. So we have to measure it somehow. So if you just say sunburn, that's probably not good enough. It's a measure of it, the amount of it. And sometimes the problem will say, we're going to measure it from 1 to 10. Okay, so the measurement from 1 to 10 on each person's arm. So be careful about response variable. It's a number. We got to use a number somehow. Make sure you're measuring something. Experimental designs. Let's design this experiment. Experimental design must include randomization, clear description of treatments, and measuring what you're measuring. Now, we don't often ask, I don't know in your class, if you do the trees for experimental design or if you write a paragraph. We haven't seen many just flat out design the experiments recently, but you never know. It might be on the exam this year. So let's deconstruct and context. This is about sunscreen and sunburn. Oh yeah, this is a big one. when you do your final analysis, don't just say compare results, compare levels of sunscreen. Talk about what you're comparing. What is it we're going to compare? Okay, so fun in the sun. So we're going to randomize the subjects to treatments. Let's do this in the chat. What are you going to use to randomize the subjects to treatments? What do you think? What do you think? And you can just say what you like. Chakri, just make sure you're not giving me DMs here. Hat method, random assignment. So how are you going to do it? We get hat methods, random number generators, roll dice, paper slip method, coin flip, a lot of things we can do. So let's deconstruct some of those. One way you can do it, take 100 slips of paper in a shaken bucket, 50 or O, 50 or N. If you get an O, you get the old. If you get an N, you get the new. Everyone picks into the bucket, that decides. Eeny, meeny, miny, mo, that is not a randomization scheme. I will add that for Nesties, eeny, meeny, miny, mo is not a randomization scheme. I remember a couple years ago, I read a question about twins that got acne medication. And we had a couple students who said, have the twins play rock, paper, scissors to decide who gets what. And that was deemed not acceptable because it was deemed that rock, paper, scissors is a strategy game that is not random. We can debate that, but that was the rule. But also, coin flipping. Coin flipping can be a little problematic unless you say it very specifically. And here's why. Let's say I have 100 volunteers. They're all lined up. They're waiting to get their treatment. And I say, heads, you get the old treatment. Tails, you get the new treatment. And everyone comes up to me. I get heads, tails, and I'm giving out the treatments people. Heads, tails, heads, tails, heads, tails. You know what might happen and why this isn't random? Because it doesn't ensure 50 and 50 in each group. And if I want 50 and 50, what's likely to happen is that the people at the end of the line will all get the same treatment. Because you know you're going to get the 50 heads before 50 tails or vice versa. And the people at the end of the line, it's just going to be, oh, take the other one. So therefore, it's not random. So if not every person has an opportunity to get both treatments and every subgroup has that opportunity, it's not random. So if you do coin flipping in experimental design, you have to be specific. And here, it's probably not going to fly. The slips work really great. Treatments, new and old, applied to the body, and results after 2 hours measure the extent of sun exposure to arms. Okay. Let's take a deeper dive. Look at some other words here. Could we use a placebo? Talk in the chat. Could we use a placebo here? Give me a quick explanation of that. I think we're okay on time. So let's do that. Tell me about placebos. What do you think about placebo? Could we do it? Could we have a placebo? Yes, we could. Yes, yes, yes. Okay. We could have one, but it's not necessary. Okay. Could we use one? So I see a couple things going on here. So first of all, could we and should we? There's two different questions. So first of all, could we? I'm not going to go back, but if you go back to the original question, there was a phrase there that said something like, you can't tell which one is which. The differences between the new and the old, you can't tell which one's which. They have the same look to them. So you could use a placebo because you get the old, the new, and a placebo, and they would all look the same and people wouldn't know which one they got. You should, and we can go down this one, if people's behavior would be changed if they knew they had a placebo. Oh, by the way, you have placebo sunscreen. Oh, hell, I should stay out of the sun, right? Oh, heck, I got to change my behaviors. So could and should are two different questions. If you could, if it's possible to give a placebo, then go ahead and do that. Okay, could we improve this design? Anyone think of a way we can improve this design? And I know I only have 4 or 5 minutes left, so I'm going to stare for like 10 seconds. There's a way to improve this design. I have an old treatment and a new treatment. Double blind would be cool. We're going to talk about blinding. Increase sample size. That'd be nice. The design. Here's how we can do it. I have 2 arms. Oh, someone just said it. Sonia, you're awesome. Match pairs. Let's take a look. This would be match pairs. How would match pairs work? Could it be match pairs? And it could. Procedure. Each experimental unit serves its own control group or creates pairs of self-similar blocks. I have 2 arms. So I come up to get it, and let's see what I have it. I think I have it here on the screen. Why? It helps reduce the variation. So here's what you could do. The subjects flip a coin, and that determines which arm you get the old one on and which one you get the new. So I give you 2 little bottles, and you don't know which one's which because they're just said left and right. Old goes on your left, new goes on your right, and tails does vice versa. And at the end, you compare the difference in exposure between the arms. This one's redder than this one. And then I don't have to worry about if some Irish people happen to get the one kind and some darker skin people get the other kind. Then I'm just comparing arm to arm. And I can compare the results that way. Match pairs. If something can be match pairs, It should be matched pairs. Just keep that in mind. Very nice. Blinding. Someone brought up blinding. What would blinding mean? Well, let's see. Could the sunscreen experiment be double blind? Well, yeah, if those using the sunscreen, the subjects, or those evaluating it, the evaluators know who don't know. Wait a minute. If neither knows who received each treatment, this experiment could be double blind. People don't know because they're just going to be in labeled bottles, little barcodes on them or something. And the experimenters don't have to know. They could just see it on a computer spreadsheet. They don't have to know. Somehow someone knows in a computer, but they don't have to know. The evaluators don't have to know. So it could be double blind. And the purpose is it reduces bias. Two ways. On the account of the subject, it doesn't change their behavior. And the evaluators don't say, oh, that was the new sunscreen. Look how good your arm did. You don't want to let people know, and that change what happens. Yeah, Jackson, put the sunscreens identical bottles. Usually they just have little barcodes on them, and that's how someone knows. They scan the bottles, and that's how they figure out who has who. All right, this is our last choose your best. Last one, and I'm almost done. A researcher suggests that we improve the design by blocking by ethnicity. What does this mean? Okay, again, there's going to be 3 on this one, so you're going to hold off on your answer until we do the big waterfall. What does it mean to block? Split the volunteers into ethnic groups, run separate experiments. Ensure the ethnicities are equally represented in treatment groups. Randomly assign volunteers to ethnic groups. All right, hold on to it. 5, 4, 3, 2, 1, go. We got a lot of A's, C, some B's. I'm glad no one is saying C. Do we realize the silliness in C? I'm going to assign you to the Caucasian group today. You can't do that. Can't do that. A or B? It is A. Blocking means you're going to split the volunteers into ethnic groups because I suspect that the sunscreen may work different on different groups. I'm going to put them into different groups, and I'm going to run separate experiments. And it might turn out that you find this sunscreen works great for certain ethnicities and not so great for others. Essentially means break them into groups, run separate experiments. You want those groups to be as similar as possible and then randomize within those groups. So just to end with that, blocking, if you drew, so how can we design by blocking? Blocking a group of experimental units that are known before the experiment to be similar in some way. And then the random assignment is within each block. And if you had to draw it, it would look something like this. We haven't had to draw one for a while. But you have the younger group. I did younger and older. I don't know why. I don't know why I didn't do ethnicities here. So probably change this one. But we have a younger group and an older group. That could also be random assignment, old, new. Please write random assignment and how you would do it and compare the sun exposure differences. And you might reach different conclusions in each group. And that is absolutely okay. All right, folks, now go forth and be awesome. And thank you very much for the time. I know that was whirlwind, but I hope that you got something out of that. And at this point, it is time for your last presenter. The wonderful Beth Benzing is going to speak about probability. Thank you all very much.
That was awesome, Bob. Thank you so much. I really enjoyed that. We did a sunscreen problem today. It was not on experimental design, but it was with sunscreen. And it was a little disappointing how a small percentage of people that wear sunscreen. Anyway, thank you very much. That was awesome. To get started, we are going to talk about probability. Oh no, this is my nemesis. Sometimes I'll read a probability question and I see my students, their palms are getting sweaty and they're like, oh, what am I going to do? I don't even know where to start. Well, sometimes I can understand the pain because probability is sometimes a challenge, but today my goal is to give you a little toolbox of a little kit of just some strategies that we can possibly use to build your confidence of diving into a challenging probability question. I'm going to do 3 probability questions with you all today. The first one is we have a person who has a job just a few bus stops away from his house.
Beth, are you trying to share your screen?
That would be, no, I am not. Thank you so much.
That's all right. It happens.
Third in line, I guess. That's what happens, huh?
Yep, that's all right.
Thank you, Lee. Am I sharing now?
Yes, you are.
Thank you. All right, let's try that again. There you go. There's our nemesis. There's our difficulty. But we're going to start with the toolbox. Thanks, Lee. Okay, so let's get started here. Here's our problem. I'll sort of summarize it for you as you read it on your own. We have a person who lives a few bus stops away from his house, his work, his job. And he notices that it will get there faster if he uses the bus, but there's a lot more variability due to traffic and other things that are existing on the road. And he estimates that the average time to get to work is approximately normal, centered on 12 minutes with a standard deviation of 4 minutes. Well, he could also walk to work. And he calculated that this is also approximately normally distributed with a center at average of 16 minutes and a standard deviation of 1. So the question is, what is the probability that the bus will be faster than walking? Well, let me just summarize some things. They gave you 2 different distributions. And the question is, what is the probability that bus will be faster than walking? So actually, I'm going to give you about 20 seconds just to sort of process. And my question that I want you thinking about is, what distribution do you want to be thinking about to answer this question? I'll let you think on your own for about 20 seconds. So they gave you 2 different distributions, but we need to be thinking about the distribution of combining the 2. So if I need to compare 2 times, I actually want to subtract the 2 different possible times that could exist of a randomly selected time when walking versus the bus that day. And I want to take the differences and study all possible differences of walking minus bus. Now, I want you to go to your chat, and I would like you to think about right now, what do you think the center of this distribution would be? And go ahead and add it right in the chat. In fact, my chat went away, so let me pull it back up here. Okay, so what do you think? Go ahead and put in the chat what you think the center of this distribution would be. Okay, we got some good guesses here. We got 4s and 12s. Okay, so here again, we're studying the differences of walking minus bus. So we're going to combine 2 different distributions. And we're thinking about this just one distribution. And many of you were correct. In this case, our center is 4, which means that it means that walking, am I going to get this right? Yeah, that the bus arrives 4 minutes earlier than walking, right? It takes the walking 4 minutes longer than the bus. Good. Now, we also need to get the standard deviation. A very common thing students will do is they'll add standard deviations. If you add the standard deviation, the spread of that distribution will be significantly larger than what we need. We are going to square root the sum of the variances in this, and that's not a super intuitive. And hopefully your teacher has sort of shared this with you before, but it is the square root of some of the variances in this case. And I got the square root of 17. So that's phase 1. So phase 1 is, what is the distribution that you should be thinking about to even attack this question? Now, the second part, and I'm going to give you about 10 seconds to think about, what part of my graph here do I want to shade? Do I want to calculate? What part do I want to find the probability of? So, oh, I got one more thing. Hold on, let me get the distributions. Do you see it? Beautiful. There it is. Okay, so I'll give you about 10, 15 seconds to think about, where do I have to shade this distribution to calculate this probability?
No good. There's an
I think someone's still muted, or not muted, but let's take a look. I think, and at this point in time, yeah, we actually want to shade to the right of 0. 0 means it's a tie. Yeah, awesome. So a lot of times, I've given this question several times to actually classes before, and many of them will actually do what some of you have said. They think it's less than 0. So let's think about some dots that work. And our job is to see, when does bus arrive faster than walking? So if bus takes, let's put 15 minutes to get to work. If bus is 15 minutes and walking takes 10 minutes, who got there faster? Well, in that case, the bus or the walking got there faster, and that would be negative. But let's look at the 4. So if you're at 4 minutes, 4 minutes would be, well, maybe walking took 14 minutes and bus took 10. So who got there faster? Walking. So this is a good option, 4. And you can try some other examples, but we are going to shade right. And that's the key. So right now, I think the easiest part is actually doing the calculations. So starting this problem is the challenge, creating the distribution, shading it correctly, and then I'll finish with the calculations. We're going to create your z-score. You're going to calculate your z-score, meaning you're about 0.97, about 1 standard deviations below the mean. And when you calculate this, you'll get about 83% chance of this occurring. What do you need to show the reader? Let's show you. Here we go. Oh, by the way, that's observed minus expected. A lot of times students will not say 0 way over here. Isn't 0 supposed to be in the middle? No, the difference between them is 4. So this is a tie. They get there at the exact same time, and that's way off to the left here. So be careful of that as well. So let's take a look. What do we need to show the reader? You need to show the reader the center of the distribution. Your mean is the 4. You need to show the reader your standard deviation. You also need to show the reader where you're shading. You need to show the person that's reading the situation that you understand that for walking to be slower than bus, that we need to shade to the right of 0. By the way, this wasn't brought up, but a person could have done the same problem with bus minus walk, and then you would have had -4 in the center, and your shading would have been the opposite direction. But I like to think of it as positive values. And then the last thing, of course, is your final answer. For this particular question, I noticed some good questions here coming up. I probably didn't hear them all, but do we need to show conditions for this? No. Probability questions typically don't need to show the conditions at this point in time. If you do need to show exactly what I circled here, right? The distribution itself, and then the final, and then the shading, and then the final answer. Okay, we got 2 more. You guys ready? Let's try 2 more challenging probability questions. Thank you guys for participating. All right, here we go. We have a bathtub, and it's like one of these fancy bathtubs that will set the water temperature for you. Very cool. It's like a baby tub, which is great for families and with new moms and dads, and washing their babies. So this is fantastic. But it's set in Celsius, and they need to change it to Fahrenheit. So I need you to describe the distribution of the water when we change it to Fahrenheit. So I'm going to ask you guys a question here. In the chat, I would like you to share with me, what do you think you need to share to the reader and put in the question when it says describe the distribution? What do you think it's looking for? You don't even have to give me an answer. I just want we need to show this, or what do you think you need to show to the reader to answer this question? Describe the distribution. Okay, I see some fun things here. Good. The sock's good. Center shape spread. Maybe a possible outlier. Good. See socks, yep. Center shape spread. Fantastic. Okay. Yay, you guys got it. Great. Good job. In this case, the key to this problem, thank you. Fantastic. Yeah, the key to this problem, so just so you understand it, is, hey, we're thinking about all possible Celsius degrees, all possible Celsius temperatures, and we need to convert it. We need to convert a Celsius degree to Fahrenheit, right? So even let's think of, a logical one, 0 degrees Celsius, we actually know, right, is 32 degrees Fahrenheit. So just think about like a logical conversion that you can think about. So in this case, if the center is at 34, what would be your mean and what would be your standard deviation? So those are the 2 big things that we're looking for, but center shape spread is certainly the key. Really good job, guys. Let's do it here. The center, in this case, turns out to be exactly the 32.2. Most students do get the center with success. And then we should describe the spread with standard deviation. And in this case, let's see if you guys got it, and I'll tell you what the key here is. I'm glad we're doing this one because this actually came up with my students today. So in this case, we are just going to multiply the standard deviation of Celsius by 9/5. And why? Very good. Thank you. Good job. We are not going to, the spread of the data does not change when you add or subtract constants like 32. So really good catch there. Very, very common multiple choice question right here. So we want to make sure we get that. I think by just sharing that the shape is normally distributed, by showing the shape is fantastic, but you're also welcome, instead of drawing it, but just to show this capital N, show for a normal curve. So capital N, and then the notation with the center and standard deviation here. But the shape is good enough. That shows that you understand the new distribution of Fahrenheit's will be normally distributed. Okay, so I think part A is pretty important, but even if you don't get part A correct, no worries. Use your same answer to go forward and you still can earn full credit for part B. And part B is really just a chapter 1 question. So it's good to finish the questions. Don't skip part B, even if part A may have been a challenge for you. Write something down for the standard deviation. Okay, yeah, you already said these, so that's fantastic. All right, let's do part B. All right, part B, according to Babies R Us, which I don't even think exists. I think maybe it does exist. I think they merged with Target or something. I'm not even sure. Anyway, the temperature of baby water should be between 90 degrees Fahrenheit and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby is safe setting is used to meet the recommendation. Okay, so I actually will go quick because I want to get to that last question here that I have for you. Oh, I forgot. That's right. I think the part that I'm glad I highlighted that. I think that's really the key to part A, what I highlighted there. Okay, let's go to part B. You have to, there's the ultimate goal here is to find the area of the shaded region in my image there. And to do that, let's find our z-scores and find the possible final answer. You don't need much to do this. You definitely need your z-scores. You need to show your inequality, maybe of the shading here, and then your final answer. For my class, I always like to bubble things that you don't need to show the reader, but this is just for your sake. If you're using a TI device, how to calculate the 78.4% as the answer. Okay, I think we're ready for question 3. What do you guys think? All right, question 3 is a little different as well. All 3 of these are going to be a little different. Okay, multiples. I like this because I'm actually an identical twin, so this is a fun problem for me. And we're doing lefties, which came up with Miss Lataro earlier today. Okay. Here we go. All right, approximately 3.5% of all children born in a region are from multiple births, twins, triplets, etc. Okay. Of the children born in that region who are multiples, 22% are left-handed. Of the children born in the region who are from single births, 11% are left-handed. Well, there's a lot of questions. A, B, C, D. Oh my goodness. So in this case, all of a sudden, as soon as you see these among a certain group, given this group, 10% are going to have this. We have this conditional probability we refer to this. And my strategy in my classes is no formulas, no memorizing. We are going to think logically about this problem. And the best way to do that in my eyes is through just a single table. And in this case, just set up your table and let's put all of the data into this table. And from that, we're going to be able to answer every single probability question that exists. So our topics are left-handed, not left-handed, multiple births, not multiple, single birth. So those are our topics. And let's put, 100 participants, right? 100 participants from this region. All right, let's get started. Well, it says 3.5% of the children have multiple births. So therefore, single births would be 96.5. Okay, then it says 22% among the multiple births are left-handed. So we're going to fill in this square. And then the remaining of them, of course, will be here. All right, last line here. Let's go. The children born in this region who are from single births, 11% are left-handed. So we're going to do 11% of the 96.5. and then there's the remaining. Okay, so from this table that I have here, we're gonna be able to answer any probability question around. So it's really helpful, and I'm not gonna use a single formula to do it. All right, so here we go. So all these challenging, so A and B, we're just gonna use this table. What's the probability that a randomly selected child born in the region is left-handed? Well, in this case, because of time, I'm going to continue on with their answers here. Left-handed is going to be, right, these over here. Hopefully you're getting that. All right, let's read the next question. And a lot of times it's just reading the question correctly, right? What is it asking for? That's the hard part sometimes of this course. What is the probability that a randomly selected child born in the region is a child from a multiple birth given, so this is like among this group, given that the child is selected left-handed? So here's some really nice notation that you can use, right? This is the probability that someone is a multiple given they're left-handed. So what are we focusing on? We're focusing on all the lefties and the probability that they are among the lefties, what percent of them are multiples. And there we go. All right, 2 more. You got this, guys. Let's take a look at the last 2. All right. A random sample of 20 children, fixed term, 20 children, like 20 basketball shots, 20, right? 20 attempts, 20 children in the region will be selected. What's the probability that the sample will have at least 3 children who are left-handed? Well, I am hoping at this point in time, I'm hoping you're something shouting out at you. I'm hoping you're thinking that this is a binomial. Binomial, right? Now, I actually added these 2 questions at the end just to give you more exposure to more probability questions. But it's actually a little bit of a challenge because I've given this to my students before, and many of them will, you know, show off their knowledge and share with me. It's 20, choose 3, right? How many different combinations of the 20 people could be left-handed? And then the probability of being left-handed, 3 of them, right? 11% to the 3rd, and then 1 minus 11% to the 17th. But be careful. Does anyone know why this is wrong? Does anyone want to share in the chat? I'll take actually anything. Would anyone like to share in the chat why this could be incorrect? I'll give you a hint, some wording here. Yeah, good catch. Thank you, Leanne. Yep. At least, yeah, darn. So in this case, this is a very, very common answer that I'll get from my students is this, but it's at least. Be very careful. They will do this to you sometimes. At least is a very common AP stat word, at least and at most. Yep. So in this case, we're going to do the probability of getting 3 plus the probability of getting 4 plus the probability of getting 5 all the way through 20. Well, a quick way to do that is 100% minus 1. No one's lefty, or 1 of the person's lefty, or 3 people's lefty. So yeah, I think that would be a quicker way to do it. And there's my final answer. And I know my time is getting short here. Just a reminder, the bubble is not needed. They do not need calculator talk. But if you're going to do 20, choose 2 in the calculator, it's math prob to find that command. Okay, my time is running very short, so I'm going to go through the last one really quickly. I added this at the last minute because it was just another exposure to another probability question. And what is the probability of selecting the first child who is left-handed by the 3rd selection? Well, this hasn't come up in a while, so I thought I would share it because it might come up maybe this year. And this is actually a geometric. So in this case, it would be the probability of a success, first person, yay, lefty. Or the second person, meaning first person, no, lefty, yes. Or the 3rd person could be a lefty. No, yes, lefty. So in this case, again, it's not a common skill, but could come up. It is an expectation that they're expecting of you, is a geometric, and it's been sort of a focus for the last couple years. And I just want to share with you something in the formula sheet is the mean of a geometric, is not emphasized, but on the other hand, it is in the formula sheet 1 over P. And the meaning behind this would be, on average, in the long run, it would take about 8.7 picks before I would get a lefty. And then here's the standard deviation formula as well. That would be on average the distance away from the mean of how many lefties you would take. Anyway, I think that's time. We promised you we would end at 8:30. I want to wish you the best of very much luck on, but you guys won't need it because you're going to continue to work really, really hard for the next 7 days. We're very excited for you, but best of luck on May 7th. And thank you for joining us today. At this point in time, I think it's probably best that we take questions, but our session is over officially because it's 8:30. So I want to remind you all that we will be recording this and pushing out the recording in email in the next few days. And thank you so much for joining us today. What do you think is best? Let's see here. Let's do some possible questions maybe through the chat. Why don't we get started with that?
Yeah.
Thank you
Yeah,
for joining us, guys.
Yeah, the only question that I saw in the chat early on was when do you use a Z test versus a T test? And that's definitely a common question students often have. So Z is used for working with proportions and T is for working with mean. So that's the short answer to that question. We won't get into why and get into the weeds of that, but that is the short answer. Z for proportions, T for means. Did you see any questions in the chat, Bob?
I
that
didn't
came
see
to you
anything really.
directly?
Yeah.
No?
If they
Okay.
have any, feel free to type them in, folks. And it doesn't have to be about what we did here. It could be like Z versus T, about anything else that's on your mind.
You know, I went through that computer output really fast. So if you're like, I don't know what those numbers were, we can even pull that back up.
Yeah, yeah.
Oh, there's a question about your shirt there, Ms.
Yeah, from
Bensing.
nerds or us. Oh, no.
Yeah, every year I have a lot of stat t-shirts, but this one says I'm statistically significant.
Yep.
Jackson, go ahead. If you want to type it, if you want to open it. Oh, there he
Yeah.
goes. Yeah, do it, Jackson.
I've got it. Wait, is my mic on?
Yeah,
Yes,
you're
you
good.
are. We can hear you.
Okay,
Yep.
okay. So this is actually okay. Wait, actually, I gotta get this set up. It's weird. I got 2 screens, so I'm looking at this screen right now. So I'm just gonna.
He's watching the draft
Yeah, I'm watching the draft right
and the
now.
Sixers. There's a lot
Um,
going on. And the Sixers.
So I just wanted to ask. You brought up earlier how when you like not to use too many like fancy words. Mr. Lockle
Lucia, yeah, that's fine.
doing experimental.
Yep.
Design, like
Yeah,
experiment.
sampling and experiments, kids tend to write a lot of fluffy language. Yeah.
So my question is, when you're writing that question down, should you focus on like what you know at your heart, even if it is like a fancy way of saying it? Or is it like, should you go for like the common answer? So like for the Villanova question, should you say, oh, it's biased because the sample has a non-response bias, which is what my teacher taught me to use? Or should I just say, oh, it underestimates the people who come later to go to the stadium because they don't
So,
wait time to
and
get in?
Beth and Lee, feel free to chime in. I tell my students whenever the word bias comes up, it must be accompanied by overestimate or underestimate. So saying it's biased because there's non-response is not, it depends on the question, but I'm going to guess that's not going to be sufficient because usually we want you to tie that to what we're trying to estimate. So let's say there was one with non-response. Well, if the non-responders were somehow fundamentally different than people who would respond, then we'd be likely to overestimate or underestimate something. So what is it we're trying to estimate? So if we're trying to estimate the proportion of people who I don't know if I can't.
I'll give an example. So one year there was a question about, I think, recycling, and the question was asked by the environmental science teacher, right? And so, there's going to be bias in the results because of the fact that the students are probably not going to necessarily lie to the environmental science teacher, especially if that person's their teacher. And so the estimate would be biased. It'd probably be higher than what it actually is because of the students lying and saying that they recycle when they don't. So that there's a justification for the direction of the bias as well.
Okay.
Yeah.
Yeah, it's just in our class we use a lot of fancy words when we do it, so I didn't know what
and you don't have
do.
to. Yeah, and it's very and you can use very fancy language, but I have seen a lot of students who use fancy language and just throw every vocabulary word they know at the explanation. But if it doesn't have context in it, if you haven't discussed what the problem's about, like recycling, like Lee said, if the response is not about recycling, then generally it's not going to get an essentially correct. It's at best going to get a P. You need to tell us why this matters when we're trying to estimate recycling habits and whatnot. Okay. So Jackson, we
Thank
hope
you.
that answered your question. Do you have a follow-up? And I know we have another question in the
Yeah,
chat.
and
this
I've
was
got
ve-
a couple questions that were sent to me in direct message also.
Okay. So we're going to answer some others. Go ahead, Lee.
Yeah.
Yeah, go ahead, Lee, and I'll answer the other one now.
Okay, so I had a question about let me see, hold on, it's up here. So when doing probability, right, and doing conditional probability, the question was, do you have to use the notation, you know, like given that with that vertical bar, or do you have to use notations like intersections and unions and things like that? Do you want to answer that one, Beth, since that was your area? Your thoughts on using notation when they write in a free response question?
Yeah. So I think you guys actually answered it for us. You guys said you need to hit center, shape, spread. So, you know, notation, do you really need it to say capital N parenthesis, you know? So no, you don't. You know, just showing a beautiful picture of a normal curve. You don't even need to say it's normal curve, because you showed the reader, you understand that you're dealing with a normal distribution. You have to show the reader, you know, what the center might be, the mean, and the standard deviation. But necessarily the notation, no calculator talk, but you know, using, even if it's, I did see a question as you were talking, Lee, sorry for my hesitation.
That's
but
okay, that's
a
okay.
question about a binomial and a geometric. Binomial will use capital B, but you can just use the words. This is a binomial distribution that has, you know, 10 attempts, and the probability of success is 0.6. So notation is welcome, but I don't think it's always necessary. You can use the words or pictures to illustrate your understanding with center, shape, and spread.
Yep. And also, even just for a probability question, you know, if it says at least 3 and you want to write, you know, 3 or more instead of X greater than or equal to 3, I mean, that's okay because it's showing kind of a boundary and a direction.
Lee, I know
so-
there's a lot of other questions in the chat that are really good, but I want to go back to your original question, which was about the conditional probability and the use
Yeah.
of formulas. Generally, no. However, if you use a table, and I'm going to make up numbers, let's say that the probability comes out as 0.115 over 0.826 for whatever reason, and that equals some decimal. It's very important that you show that numerator and denominator and then say it equals a decimal. If you just divide your two things in the conditional probability and don't show us where they came from, you won't get credit. So I'll just leave it at that.
Can we stick with the just real quick, because I see
Yep.
it here. What's the difference between a binomial and a geometric? Is that okay
Yep.
if we
Yeah,
okay.
go for it. That's yours.
So the binomial was the letter C for my problem, where we had 20 attempts. What's the probability that there were 3 lefties, right? If we randomly select 20 people, that is a binomial. Binomial, you know, a fixed number of outcomes. The probability doesn't change. Every single pick is independent from the next. It feels like a geometric, but a geometric is actually you end on a success. So that would be, I'm going to keep on picking individuals until I get a lefty. So you're ending with the success. So it's failure, 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 success. And my question is the absent-minded professor problem. You know, what's the probability until you get the door open with your set of keys if you lose track of your keys? So you end on a success. It's not, geometrics typically don't come up in our AP curriculum, but it has been a point of emphasis in the last few years since COVID. It still hasn't really come up too much, but I added that letter D in at the last minute because I just wanted you to have as much exposure as possible with geometrics. But you're ending on a success. Binomials, the success can happen anywhere in the 20 picks.
Lee, if it's okay, I'm going to take the question from Mallory. Oh, actually, why don't you take the question from Mallory and I'll take the question from Shakri, because that was kind of my thing.
Okay, so I'll take the question from Mallory. It says, if you use a calculator instead of the formulas, do you still have to show the formula with the numbers or state what you put it or state what you put in and what you get out, besides chi-squared and goodness of fit. So I would say if you were, obviously, if you're doing a free response question, it is perfectly fine to use the calculator for that, for doing the work in terms of calculating the test statistic and the p-value. So there, you definitely need to name the procedure. If you were to try to write down a formula, it better be correct, because if it's not correct or the numbers are not correct when you substitute them in, then that's going to hurt your score. So if you're not quite sure how to put the numbers together in terms of a formula for a free response question, it's best just to use your calculator. So, you know, say you're going to do a 2 proportion z-test, which has a bit of a complicated formula. Just use the calculator to do that one. Any
Yeah,
other
I'm gonna be
thoughts
more,
related to that?
yeah, I'm gonna be more emphatic about that. When I'm doing chapter tests with my students, I do make them do the formula, because you notice they come up in multiple choices sometimes. We need to respect the formula. On May 7th, if there's a hypothesis test or a confidence interval, do not write the formula. Don't even attempt to, because the rubrics will just say the student reports the test statistic and the p-value. The formula is not necessary. If I were to make a pros cons list, there's no pros to writing the formula, and there's a lot of cons, because if you write it incorrectly, there's a ding. Whatever you write, we need to check. All you got to do, it's expected you're going to have a calculator, write the test statistic, p-value. It's time consuming to do that. You don't have all this time. So I'm emphatic. Don't even attempt to. Is there? You can debunk me on that, ladies, if you like. But that's
No. I mean, I agree with that. But in case you're like wondering, well, what if I get one of those multiple choice questions where I have to actually figure out how to put
Sure.
together the formula? I'm just going to show you the formula sheet here. I put the link for it in the chat. I call the 2 items in this box, the standardized test statistic and the confidence interval, I call them the general recipe, right? And then you're going to be substituting different ingredients into that recipe. You know, your statistic could be p hat, maybe it's x bar, maybe it's a difference of 2 different sample means. And then the standard error, the statistic, this piece of the puzzle or the recipe, you get from the second page, right? So it depends on whether you're working with 1 proportion or 2 proportions. And, you know, it depends on whether you're working with 1 mean or 2 means, right? In terms of what goes into that standard error, that statistic. And the one thing that I think is really nice is there's a clue here about when you should use this second one that's down here, right? Notice it says when P1 equals P2 is assumed, that's your null hypothesis. If you're doing a significance test for a difference in 2 proportions, right? It's right there. So I just want to point out that if you are trying to figure out how do I put those pieces together, they're right there on the formula sheet for you that you can substitute into the general recipe.
Awesome. I'm going to take this question about blocking and stratifying and try to keep it brief, because I know we're getting, and seems like there's a couple other messages going on. Blocking is for experiments. Sampling is for surveys and data collection. The reason we block is because we believe that the 2 groups, and I always go to like a drug study. Let's say I have a new headache medicine, and I think it might work differently on males and females. I'm going to block by gender, and I will do separate experiments for them both, because I think they might react differently to the drug. And I might find out that there's headache relief in general in females in the experiment, but not in the males experiment. And the reason we want to block is if males and females were mixed together in one experiment, then I may not see an effect at all, because there might happen to be, by randomization, more males and females in the different groups. And because it works for some and not for others, I might reach a different conclusion. So I block and I split things up because I believe there might be differences in the treatment groups before I start my experiment. The reason you sample is, well, think about your high school. Do freshmen, sophomores, juniors, seniors all have the same opinions on everything? If you think that the differences in opinions, there might be differences in opinions, then you want proportional representation from all classes in your school, and you'd probably take about 25% from each class. That would be stratifying by class, making sure you ensure that everyone is represented, because you think that their opinions might be different. But keep in mind there, I'm only going to do 1 survey when I'm done. I'm just going to ensure that they're equal representation from each class, and 1 survey is done. So that's a long-winded explanation for something that takes a lot longer. I haven't seen what else came up. Tests, confidence, tips remembering. Oh, there's no new questions then. Okay. Tips remembering the conditions for every single type of test interval. Okay. Randomization is almost always there. So I'm trying to think, random sampling from large populations or experiments. We're usually checking for some sort of normality. You know, those are different from proportions than for means. Proportions, expected number of successes and failures has to be greater than or equal to 10. Means we're often looking at a box plot versus what's given to us. Ladies, do you have a better way to do that? I mean, there's a lot. It's tough to get them all together.
Yeah, I mean, I would say, like you said, all of them have like some sort of randomization condition. If you're talking about experiments, it's random assignment of treatments. If you're talking about sampling, it's random sampling. And you only have to worry about that 10% check, that we sampled less than 10% of the sample size. If you're actually sampling, you don't have to check that 10% condition if you're talking about random assignment of like volunteers to treatments, right? Because that often happens with experiments. You get volunteers, but you randomly assign them to treatments. And then of course, chi-square is its own special set of conditions.
Yeah, I just to add to that is like, there's a difference between proportions and means. So like sort of the last 2 days I've been saying, okay, how do you get this to be normal, right? That's your counts. N times P is greater than 10, N times 1 minus P is greater than 10. So like, that's proportions because we need the distribution to be far enough away from 0. So think, and then the means is different, right? The means to check for shit. So I do think that middle one of normality is a big one, and they certainly will they'll try to trick you in multiple choice questions with trying to say N is greater than 30 for a proportion problem or whatnot. So I think there's a difference between proportions and means, and just sort of separate those two in your head. I think that's sort of important.
All right, I think we've got lots of people that have left, and I think we've answered all the questions.
Sounds good.
I think so. Thank you
Go
all.
Sixers.
Yeah, go Sixers is right. Thank you all for joining us. We will record this and save it, or we're recording it now, but we'll save it and push it out to you in the next few days. Thanks for joining us, guys.
All right, sounds
Take
great.
care,
Goodbye, everybody.
Bye, guys.
Bye.
Thanks for joining us.
Bye, Beth.
Bye, guys. I gotta stop recording here. There we go. Stop.